Scaling and units of measurement. When we refer to any kind of empirical exercise, at the very beginning we set up a functional relationship between the dependent and independent variables. After the relationship is stated, it is very important to go for the data collection. After the data is being collected on the separate variables, namely dependent and independent, it's very much important to have an information on the measurement of the variables. Whether the variables are unit free or if they have units, what are the units of measurement that are included in this case. And this makes the understanding of this particular module more and more important. As we go for firstly the definition of the scale of the measurement, we mean by the definition that the scale of measurement is used to represent actual dimensions in a regression model. When we refer to the actual dimensions, it means how the variables are measured and what is the domain of the variable. For example, if we want to deal with a profit function, then all the variables are measured in monetary terms. However, if the study is based on health or education, maybe the variable is measured in terms of years or the variable is measured in terms of percentage. So depending on that, the scaling of the variables are to be taken care of. And it is also important because when we interpret the results, we have to interpret keeping in mind the scaling of them. So this makes us very important to understand how the scaling of variables becomes an important issue in any empirical exercise. So from every dimension we get the variables. The variables are to be stated in the separate units and thereby we can go for the measurement. Now, as we proceed on to our interpretation of a regression equation, we see that the regression equation is estimated on the basis of y hat, which depends on two very important terms, which is called the intercept, which is a, the estimated value is a hat, and the intercept and the slope, which is also estimated as b hat. X is the independent variable. So if we go by the interpretation of this regression model, we see a hat is the intercept, that is basically the constant part when the independent variable becomes 0, and so it is independent of all the factors taken up in the model. Secondly, we have b hat, which is the slope coefficient. As we know that whenever we talk about the marginality in the context of econometrics, which means change in the dependent variable due to the per unit change in the independent variable. So this basically gets on to the concept of b hat, which is estimated value of the slope coefficient. So if the variable x changes by 1 unit, in what proportion the variable y will change, that will be captured by the b hat or the estimated value of the slope coefficient. And so it's very important to understand how x and y are measured. As we mention here categorically that if x is measured in dollars, then b will give us certain interpretation which will be interpreted in terms of dollars. But if x is measured in terms of thousands of dollars or in rupees, then b will have different interpretations. So accordingly, the variable x is very important to understand in what unit it is measured, correspondingly in what unit variable y is measured, and then only we can talk about a better or an accurate interpretation of a hat and b hat, which are the interpretation of this regression equation. Now we are actually focusing on a particular example based on the applications. And in this particular example, we raise a lot of queries. That means we want to understand what can be the responses to these queries. First of all, we look after a regression of GDP-DI. That means gross personal disposable income on gross domestic product GDP. So basically GDPI is an independent variable and GDP is a dependent variable as for the language of the statement means. The researcher uses data in billions of dollars. So in one set of the model it is in the billions of dollars, both X and Y, that is GDP and GDPI. And in another set of model, both are in the millions of dollars. So one model is set in the billion of dollars, another is in the millions of dollars. And so the researcher is asked a lot of questions. The first question is this: whether the regression results be the same. For example, when we look at the OLS property, whether the properties will be affected or not, that is the first result it wants to say. If not, why the results are not same, which result should be used more, and what is the importance of the units in this regression. That means when we look for the regression analysis, what are the importance of these units and what can be the sensible way of choosing units of measurement. Because at the end of the day, the regression equation should have uniformity in the measurement of the variables. So in order to do this, what could be the sensible way out? So particularly in this particular question, we are dealing with two regression sets. One set is expressed in the dollars, which is in millions. Another is in the billion of the dollars, and we are actually forwarded with a lot of queries about the regression results, whether the regression results will be accurate enough, whether the units are affecting any regression result or not, and what can be a more sensible way of looking at it. And that is how the queries needs to be answered. Now in this case, we refer to the interpretations based on that particular question. Here we observe that yi is considered to be the GDP, which is the dependent variable, and the independent variable is GDP di, which means x is GDP di. Now in this particular model we observe yi is dependent on xi and it's a bivariate regression model. So we have the intercept term which is beta 1 hat, which is interpreted, and beta 2 hat also, which is estimated. And this ui hat is basically the estimated value of the error term. So what has the researcher done? The researcher has collected the data of y and x in billions of dollars, and in the next model he has collected the data in the millions of dollars and the interpretation to be done in an uniform manner. So in this particular model we observe two sets of equations are needed because the units are different, and accordingly beta 1 hat and beta 2 hat are to be estimated. And accordingly we will apply the method of ordinary least squares as we have already done. So first of all, what we observe? We observe the model once more written here as yi, which is the dependent variable. Beta 1 hat is the independent variable, which is the intercept. Beta 2 hat is the slope coefficient, xi plus ui hat. Now we have to rescale the variables. Why the scaling is needed? Because W1 and W2 are introduced in this equation so that they become equal to yi star. So when I say yi star, it is basically W1 multiplied by yi. So the original variable was yi, that is being multiplied by W1, which is the weight, and thereby we get yi star. And similarly, in the independent variable also, the scaling is being done because xi star is equal to W2 into x1. So x1 was the original independent variable. So the weight is W2, which is multiplied by the x1, and we get xi star. So this W1 and W2 are basically the constants, and they are the scaling of the factors. For example, if we have billion or trillion or million, then we are actually considering multiplied by 1000 or multiplying by 10,000 in order to get the uniform scaling. So yi star and xi star are rescaled, and this rescaling is done because x and y are not uniform in the units of measurement across the two models. So what we observe? yi and xi are measured in the billions of dollars as we have started with, and if we want to express them in the millions of dollars, then we will have yi star 1000 into y1 and x1 star 1000 into x1. So here we observe W and W2 are the same but may be different in some cases. and thereby both the dependent and the independent variables are rescaled as per the weightage of W1 and W2. This goes back to our very important derivation because how it affects the entire estimation exercise. So again we observe in the original model we have yi as the dependent variable, beta 1 hat is the estimated value of the intercept, beta 2 hat is the estimated value of the slope coefficient, xi plus uy hat. So what we observe in the step 1, we consider the yi star to be w1 yi, which means w1 is the weight attached with the y1, and x1 star is w2 into x1, which is again the weight attached with x1, and that is what we get in the step 1. As we do in our ordinary least square methodology, we take all the variables, the deviation from their means. For example, yi minus y bar, xi minus x bar in this way, and we make them represented in the small letters. So similarly, we do the same thing here. So we mention taking deviations from means friends from the sample means, we get small yi star. So now instead of writing capital yi star, we write small yi star equals to w1 yi, which is absolutely considered as the initial value of the variable, and similarly xi star equals to wy xi. So accordingly we get yi star and xi star so that they are converted to the deviation from the means. Now we go back to our very original expression of beta hat 2, which means estimated value of the slope coefficient. So in a normal model which is not rescaled, keeping the originality of the model, we observe that the formula of beta hat is summation yi xi by summation xi square. In this case, yi xi are not existing in that way. They are converted to yi star and xi star because they are the scaled variables, because the w's are attached with them. So accordingly what we get the first step as summation of yi star xi star divided by summation of xi star square, which is the original expression of a beta hat coefficient under OLS. Now instead of writing yi star or xi star, we are writing in terms of weights. We are just expanding the expression. So instead of xi star, we write w2 xi, and instead of yi star, we write w1 yi. So w2 xi and w1 yy we are writing. Similarly, divided by summation of w2 square xi star square. Because xi star is in the square form, so accordingly weights also will be in the square form. That's why we write w2 square. So after simplification, we end up with the ratio of the weights, which is a relative measure, which is basically the relative measurement, which is w1 by w2 into beta hat 2. Because this beta hat 2 is actually coming up after cancellation as the original equation, which is summation of xi yi by summation of xi square, and by taking weights outside the summation sign, we get the relative of weights, which is w1 by w2, and that appears as the step 2. So as we now proceed further to some of the important statistical results based on the scaling, we observe that again we start with our original model where yi is regressed upon xi and beta 1 hat and beta 2 hat are the slope coefficients. Then we go to the step 1 where the rescaling is being done. That means original yi is converted to yi star and original xi is converted to xi star because they are multiplied with their respective weights, that is w1 and w2. In this case, as per our example, w1 and w2 are same, but it might not be same in all cases. Next, we take the help of estimated coefficient of beta star hat 2, that is after the scaling of the model is being done. So after that we get beta star, and just now we have derived in the step 2, which is w1 by w2 into beta hat 2. So accordingly we can also represent beta hat 1 as w1 as beta 1 hat. That means beta 1 hat star is the estimated value of the intercept term, which is also associated with only W1, as we can see in this particular equation or in step number 3. If we want to comment about the sample variance, because that is the estimated variance, population variance is unknown, we estimate it from the sample, so we get sigma hat star square, that is also equal to W1 square sigma hat square. So again we come back to the equation number 4 or step number 4, which says the same, that sigma star hat square also will be multiplied by the weight. So W1 is considered to be the weight, that is attached weight population variance. Next we have step number 5. So in step number 5 we observe variance of beta hat star square, which considers as W1 square variance of beta 1 hat. So whether the variance of the intercept term or the variance of the slope term, they are getting inflated by the value of the weight. In case of the intercept term, it's only W1 square, and in case of the slope term, it is the relative ratio of the weights W1 by W2 whole square. It's in the square form because it's a variance. And accordingly, we can also say that the correlation coefficient between x and y is equivalent to between x star and y star. That is also very important to note that xy and x star y star also remain the same in terms of the correlation coefficient. So particularly from all these discussions, we can come up to some important concepts regarding this measurement. That means we can express one measurement in terms of the other. If W1 is equal to W2, then intercept and standard error are both multiplied by W1. Particularly the intercept coefficient. But if W2 equals to W1 or it becomes 1, then all the coefficients are multiplied by W1 because W2 doesn't have any separate relevance. However, we have to be very careful regarding the last sentence which is mentioned here, that whether we transform yx to y star x star, this does not affect the properties of the OLS estimators. So the properties of the OLS estimators remain the same even if we make this transformation. So in this particular discussion, we make a point that originally the variables are converted to the scaled variables by multiplying by the respective weights. For the intercept, it is only multiplied by W1, and for the slope, it is multiplied by the ratio of W1 and W2, and accordingly, the OLS estimators are considered to be the same, or they are basically referred as unaffected. And that is how the interpretation can be done in a better manner. Now we start for the functional form of the regression model. This is very important because the variables are scaled, but we need to go for some other functional forms, for example logarithmic or linear logarithmic, to have a better estimated coefficients, particularly for looking at the statistical significance of the unknown parameters. So hereby we go for log linear model or semi-log model or the reciprocal model. So first of all, we concentrate on the exponential regression model or the log linear model. We observe that yi and xi are the independent and independent variables, but they're expressed in the exponential form, which means yi is equal to b1, which is the intercept coefficient, x1 to the power b2, e to the power ui. So whenever we refer to this b2, which is basically the unknown parameter of the population coefficient, and ui is the error term, but this is written in terms of an exponential regression model. See, if we take logarithmic on both the sides of the equation, then we end up with natural log, which is base e ln yi equals to ln b1 plus b2 ln xi plus ui. So this is very much familiar to a two-variable linear regression model, but this is basically the logarithmic model that we consider. So accordingly, we can write ln y1 equals to a, which is the ln b1, which is basically the coefficient of the intercept, plus b2, which is the slope coefficient ln xi. So when we are estimating this model using the OLS, we are getting the predicted values of y and x which are in the usual logarithmic forms, not in the original form. So thereby when we estimate the model, we have to be careful about the interpretation. So interpretation goes like this, that is, B2 measures the elasticity of y with respect to x. Because we go for due to the proportionate change in the independent variable, and thereby the elasticity concept comes in. So it is actually measuring the degree of the responsiveness, that is how the x and y are related to each other, and that is how we can go for the log linear model. So when we look at the log linear model, it's basically the elasticity part that comes in, and all the variables are converted to their logarithmic transformation. Now we move on to the semi-log model. Semi-log model in the sense is that when we have a variable like yt equals to y0 within bracket 1 plus r whole to the power t. That means if we look for a time value of a particular variable and we have r as the rate of return on that, then depending upon the step 1, we can take log on both the sides of the equation and we end up with ln yt equals to ln y0 plus t ln 1 plus r. And so this type of model can be considered as a constant growth model, because always we say that as t rises, yt will be rising but with the logarithmic power in it. So this is basically referred as a constant growth model. So what we go for that? We go for beta 1, which is considered as the intercept term, which is ln y0, which is the coefficient of the intercept term of the original model, plus beta 2 ln 1 plus r. So this 1 plus r is considered to be the slope. So accordingly, this is a semi-log model or a log linear model. And here also we make a comment that always there will be a constant proportional change in y due to the change in x. So if x changes by 1 unit, constant proportionality will be mentioned in the case of the ln yt. And that is how the entire interpretation goes in the semi-log model. So in the logarithmic model, we go for the elasticity, and in the semi-log model, we go for a constant growth model where yi and xi changes at a constant rate over the period of time. Now if we refer to this semi-log model and we want to interpret the direction of the relationship, that means depending upon the sign of the slope coefficient, which is beta 2, we can see whether y is having an upward trend or a rising trend, or y is having a downward trend or a declining trend, depending upon whether beta 2 is positive or beta 2 is negative. So if beta 2 is positive, there is an upward trend in y. If beta 2 is negative, there is a downward trend in y, and accordingly we can make our interpretation. And beta 2 always is measuring the slope of the function. So thereby we can say that yt rises exponentially or yt falls exponentially depending on different values of the beta 2. Now we go for the third type of the model, which is called the reciprocal model. That means x is taken in a reciprocal form. Instead of yi regressed on xi, yi is regressed on 1 upon xi, which means that as x increases, 1 by xi becomes very small. That means it becomes smaller and smaller and approaches towards 0 with the increase in the value of the x. And also with the increase in the time period, yt approaches the limiting value. That means it becomes 0. So this is also a case for convergence between the relationship between y and x. That is how with the rise in the t, yt approaches the convergence rule or approaches 0. This boils down to the summary of the functional forms that are being discussed in this particular module. First of all, we have a linear form which is always done usually as y regressed on x and is basically considered as beta 2 as the slope coefficient. Secondly, we have a log linear form, which means that the variables y and x both are taken in the log values. And accordingly, we go for the elasticity coefficients of beta 2. Then we have a log linear, that is either y is in the log, x is not in the log form. One of the variables is in the log form, either dependent or independent. Accordingly, the name of the function changes. If it is log linear, then the dependent is in log. If it is linear log, the independent is in log. So this is important regarding the naming of the functional form, log linear and linear log. And finally, we have the reciprocal model where x is taken up in the reciprocal form. So in this particular module, we sum up in this following manner that whenever we talk about the scaling of the variables, it does not affect the OLS properties. And moreover, the correlation coefficient becomes the same between xy and the scaled form x star y star. The conversion is done by the inclusion of the respective weights. Functional form of the model is considered because we have discussed 4 types of functional form: linear, log linear, linear log, and finally reciprocal. And also adequate examples are also considered in this case. So this module brings us to the discussions on the scale of the measurement, and it is emphasizing repeatedly that scale changes does not affect the OLS properties of the estimators.